analysis. I think you already have the idea on mechanical vibration from your course on dynamics of machine, which was taught on the previous semester. So there, single degree of freedom system vibration has been discussed. So I just ask you to what extent you have gone in that particular course in single degree of freedom vibration. You have, I hope you have learned about free vibration. Is it natural frequency, damping ratio, logarithmic decrement? These things you know. Is it?
Yes, sir.
Yes, sir.
Then forced vibration with harmonic excitation, you know. You have particularly
Yes.
solved for, say, magnification factor, resonance, then
Yes.
excitation due to motion of the base, transmissibility, wielding of shaft and critical speed, rotating unbalance. Okay, then structural damping. These things is known to you, I hope.
Yes, sir.
Did you study any other kind of excitation like non-harmonic periodic excitation or arbitrary excitation?
No, sir. But we were taught about base excitation.
Base excitation means that is a harmonic excitation.
Yes, sir. But
Sinusoidal excitation is a
non-periodic.
single frequency. But multiple frequency, did you learn
No, sir.
excitation with multiple frequency? So we'll start with whatever you have learned. After that, we'll progress to the periodic, that is non-harmonic excitation, impulse excitation, arbitrary or transient excitation. So mechanical vibration, we are first introducing certain kinds of excitation by the nature of force causing this vibration. So one is harmonic excitation. You know, harmonic excitation is a sinusoidal force with a given single frequency. That is, in harmonic excitation with 20 hertz means the frequency of excitation is 20 hertz only. There is no other frequency. That is, excitation peak is repeated 20 times in a second. Then periodic excitation. It is also a repetitive forcing function. It will repeat, same phase of the force will repeat after certain period of time. But if you analyze that in frequency domain, the signal of excitation, if you analyze the signal of excitation in frequency domain, you will find more than one frequency is possible there. Like you have a sinusoidal wave, sinusoidal force of 20 hertz and another sinusoidal force having 5 hertz frequency. Both of them are added together. They may be in the same phase. That is, at the same instant of time, both the excitation will reach its peak. That means they are in the same phase. They may be out of phase. Say 20 hertz excitation is reach its peak at a instant of time t. But at that very instant, 5 hertz excitation will not reach its peak. Usually, when the frequency is different, the phase difference will automatically come. Because at some point of time, say, both the excitation reach to their respective peaks. But the signal with 20 hertz will reach to its peak by after 1/20 second of that instant of time. But signal with 5 hertz will reach to its peak after 1/5 second from that instant of time. So automatically there will be phase mismatch. Sometimes two different sine wave of same frequency but with different amplitude will be added together to form a periodic wave. In that case, they may be in same phase. There may be also a constant phase difference between them. So in periodic signal, we'll always observe more than one frequency in the signal. How we will get that frequency, we'll study afterward. The frequency analysis is done by Fourier transformation. Now, in impulse type of signal, there is a sudden jolt type of force. You know the definition of impulse from your knowledge of higher secondary. Impulse is the force times time interval up to which that force is acting. We need to define impulse for impulsive type of force. What is the impulsive type of force? It is a force having a very high amplitude, high magnitude, very high magnitude, approaches to the infinity, but acting for a very short duration of time. That is delta t approaches to 0. So that the product of the magnitude of the force and the duration of the force will become a finite quantity, which we define as the impulse of the force. When that kind of impulsive force is acting on the system, mechanical system may exhibit a certain kind of excitation, certain kind of vibration. That vibration is due to the impulse excitation. Then transient excitation. Transient excitation, the forcing function will vary with time according to any relation. It may not be exactly sinusoidal, but it is an arbitrary relation with time. If you record the magnitude of force at different instant of time, and each instant of time is very close to each other, then if you plot those force versus time, if you do not get a curve which is a regular curve, it may not be a regular curve. And the pattern of the force is not repeating with time. Then there is another case, random excitation. There is a difference between transient excitation and random excitation. Random excitation is defined by certain statistical data. There will be certain data statistics. But transient excitation, that kind of statistics you will not see. Transient is much more arbitrary. Random, although arbitrary, there will be statistical measure. Now, this random excitation or random mechanical vibration is a completely big subject. We'll not have very much scope to discuss the random excitation within this general mechanical vibration course. So we'll not include the random excitation here, but we just mention the term in order to introduce the different types of forces for which mechanical vibration is shown. Now, types of system. So there will be linear system and non-linear system. Linear systems are governed by linear differential equation. Usually in this course, we'll consider the linear systems only. So what are the characteristics of linear differential equation? In linear differential equation, if you excite the system by a force F1, which is a function of time, the system response, that is vibration signal, will obtain as X1, which is also a function of time. Then separately, the same system is excited by another force F2, and corresponding response is X2. Then if the system is linear, we will always expect that if The actual force is linear combination of the two excitation, it is F1 and F2. So if we say apply a force which is F1 plus F2, then the response will be produced that can be expressed as linear combination of the individual responses x1 and x2. That is, if F1 and F2 are the F1 plus F2 is the excitation, then x1 plus x2 will be the response. That is, in case of linear system, principle of superposition will hold. The nonlinear system will not see this kind of characteristic. Principle superposition will not hold. And again, like random vibration, nonlinear system vibration is also a completely separate subject. We don't have much scope to discuss it here. So what we will study, basically, we will study vibration response of linear system for harmonic, periodic, impulse, and transient type of excitation. Now, types of system. Another classification of the types of system, single degree of freedom system, represented by a single mass. You have learned this type of system in your previous machine dynamics of machine course. Then multi-degree of freedom system, more than one mass. In case of multi-degree of freedom system, usually we see that multi-degree of freedom are discretized mass system. Multiple discrete mass are present in the system and you can identify each mass separately. So this amount of mass is present with this object, this amount of mass is present with the object, and these two objects are connected by this spring, damper, etc. So masses are identified separately in a multi-degree of freedom system. Another kind of multi-degree of freedom system is continuous system. In continuous system, it is mentioned separately because in continuous system, distribution of mass, distribution of other property like elasticity is continuously varying within the system. You cannot say arbitrarily that in this place this amount of mass is present. You have to do mathematical analysis for that purpose. Discrete mass elements are not identified in continuous system, although continuous system is some kind of multi-degree of freedom system. But in our discussion, multi-degree of freedom, by multi-degree of freedom system, we will mean strictly discrete multi-degree of freedom system. This continuous multi-degree of freedom system is called, we'll name that system as continuous system. Like a beam, you have learned about the deformation of beam in your strength of material course. Beam will be deformed. Beam can be deformed by applying a force, lateral force. In that beam, elasticity varies continuously from one end of the beam to other end. And if you consider the vibration of that beam, say a simply supported beam or a cantilever beam, in the vibration you also need to introduce the inertia property of the beam. The inertia properties of the beam is also continuously distributed throughout the beam. So this is a continuous system. So components of mechanical system, vibrating mechanical system. We need at least two components. One is mass, another is stiffness. So mass, this component is associated with the kinetic energy of the system. And stiffness is associated with the strain energy or potential energy of the system. Both kinetic energy and potential energy are conservative in nature. That is, they will be conserved. Now, vibration is actually continuous transformation of one form of this conservative energy, potential energy, say, to other form of conservative form of energy, say kinetic energy. Continuous exchange or continuous transformation from one form to other form and back usually causes the vibration. since this type of energies will be conserved. So they will be continuously transformed from one form to other form, but they will not be lost. So if a vibrating system includes only mass and stiffness, or inertia and elastic element, inertia element is the mass, elastic element is the stiffness, then that vibration will go on forever. There is no dissipation or loss of energy. In order to dissipate the vibration, damp the vibration out, you need certain other element called damper. A damper is a mathematical or physically model of certain part of the system where energy is getting dissipated in the form of usually heat. So this type of element usually associated with certain non-conservative forces. When that force performs some work, then that work cannot be recoverable. That is why this is non-conservative. Due to the presence of that kind of element, which we call as damper, the energy from the vibrating system will be dissipated away and the vibration will go down. Its amplitude is gradually decay. So these are the common elements of a vibrating system. But all those things are physical model, or sometimes they're mathematical representation. In actual system, most of the time you may not separately identify which part you will call as inertia part, which part you will call as a stiffness part, which part you will call as a dissipative part. All such things will be grouped together. So we need mathematical analysis. In mathematical model, we'll find separate significance of these terms. Also, vibratory motion can be categorized into three groups. One is longitudinal, where each degree of freedom vibrates along the length of the object. Another is lateral, where vibration at each degree of freedom is happening perpendicular to the length of the object, like the vibration of a beam. Torsional. Torsional vibration is observed by angular motion, vibration of a circular shaft. Longitudinal vibration, vibration of a spring. Lateral vibration, vibration of a beam. Torsional vibration, vibration of a circular shaft under varying twisting moment, time varying twisting moment. So is there any question up to this introducing comments? So we'll progress beyond this. So first we study free vibration of a single degree of freedom mechanical system. This is a repetition of what you have learned in your dynamics of machine course. In order to study vibration, we need a mathematical model. Mathematical models are given by differential equation. So in order to establish differential equation, we utilize certain physical laws. And that physical laws will be applied on an idealized system. So there is a real life system from which you'll create certain model, physical model, idealized physical model. On those idealized physical model, you'll apply physical laws to obtain differential equations, and that differential equation will be representing the system for its vibratory motion. So here we'll consider only a simple spring and a mass. Ideally, here we already have identified the inertia element and elastic element separately. How you have formed this? we'll discuss later. But somehow you have a single mass and single stiffness. That means this mass and stiffness may not be in this form, that is a single mass and single stiffness. It may be continuously distributed over the object. It may not have the physical shape shown here. It may be some other physical shape. But from that physical real life shape, we have already idealized and identified this is the mass, single mass, equivalent mass, and single equivalent stiffness of the system. So from that point of view, you want to find the mathematical model in terms of differential equation. So did I start recording the class? I forgot to record possibly. So just remind me before starting every class, so to record the class. Okay, I'm starting to record from this point of view. After that, you just note down. Okay. All right. Now we have a mass and a stiffness. We have a mass and stiffness after certain idealization of a real life system. How to get the differential equation? You know how to apply them. You will apply the Newton's law. In order to apply the Newton's law, you need to draw the free body diagram. If there is no other external force except the self weight, the free body diagram will look like this. When it is not vibrating, the mass is only hanging from the spring. Spring has certain kind of deflection. It is say delta. We will call it a static deflection. The delta is the increment of the length of spring from its free length under the action of this downward weight. When there is no motion, no vibratory motion, the object is under equilibrium, we can write the Newton's first law in this manner for static equilibrium configuration. Mg minus k delta equal to 0 and mg equal to k delta. Equilibrium means there is no acceleration of this mass. Now suppose the object is vibrating without any other external force. Vibration is measured from this static equilibrium position as x, x dot, x double dot, respectively, which denotes displacement from the static equilibrium position in downward direction positive, velocity and acceleration of this mass, respectively. Now its free body diagram will look like this. At any given displacement x, total stretch of the spring will be delta plus x. Delta is the static deflection. X is measured from the static deflection position. So delta plus x will be total deflection of the spring when this mass is at a distance x during its vibration from static deflection position. So k delta plus x is the total restoring force applied by the spring on this mass, and mg is the total downward gravitational force. So if you apply on the Newton's law, net force in downward direction will be equal to mass times net downward acceleration. So mg minus k delta plus x is equal to mx double dot. And you know previously mg equal to k delta. So finally we will obtain mx double dot plus kx equal to 0. This is one way to obtain the equation of motion for a single degree of freedom system. For a multi-degree of freedom or continuous system, you will take the similar path, but their system description will be a little bit complicated, complex. So, but the path will be similar. First you obtain static equilibrium configuration, then you obtain the dynamic configuration during vibration. Now another way to write the differential equation is using energy method. Energy method is defined in different manner. Virtual work principle is one of the method, energy method. Usually virtual work principle we have applied for the object which is under static equilibrium, which has no acceleration. But using D'Alembert principle, we can extend the application of virtual work in dynamic case also. Now, another form of energy method is Hamilton's principle. We'll learn at certain other stage of this course how Hamilton principle is written. Another form of energy method is called Lagrange's equations. So virtual work principle, Hamilton's principle or extended Hamilton principle we'll see later, or Lagrange's equation. They are basically the same thing, same statement in different form. So different person chooses different form of this energy method in order to derive the equation of motion according to their convenience. At this moment, we'll introduce the form of Lagrange's equation only. We'll just introduce, we'll not derive the actual way how to derive the Lagrange's equation. We'll not show right now. We'll come again in the discussion of multi-degree of freedom system, how Lagrange's equation are derived. But it is the form of Lagrange's equation. If we have a single degree of freedom system whose degree of freedom for vibration is defined by x, x dot is the velocity of the system, velocity of the system mass associated with the degree of freedom x. Then this is the form of Lagrange's equation, ddt of del t del x dot minus del t del x plus del u del x equal to q. What is q? Q is the net resultant force in the direction of this degree of freedom x. What is capital T? Capital T is the kinetic energy of the system, and capital U is the potential energy or the strain energy of the system. So for this example of spring mass system, we have kinetic energy half m x dot square, and we have potential energy, which is strain energy due to the spring deformation minus potential energy due to gravity. The negative sign because here we have considered x positive downward, that is in the direction of the gravitational force. But in the definition of potential energy due to gravity force, we must mention that potential energy is the work done on the object in order to move the object away from the center of the gravitational attraction. That is, if you have pulled an object of mass m above a height h from the ground, then you will say the object has gained a potential energy equal to mgh. So if you move the object in downward direction, it will lose the potential energy. That is why, since x is negative, we have mentioned negative sign here. Now q is sum of all the other forces in the direction of x. In this case, there is no other force, that is why it is 0. Now you will just put del t del x dot, which will come out to be mx dot. Del t del x is 0 because kinetic energy is not an explicit function of x, that is the displacement of the object during vibration. And del u del x is nothing but k into delta plus x minus mg. Knowing that mg equal to k delta at the static equilibrium position, delta is the static deflection. Mg equal to k delta, del u del x will come out to be kx. Substituting these expressions, you will get the same equation of motion. So this is an alternate way of applying Newton's law in order to derive the equation of vibrating system. Here, again, we'll show the method of virtual work. Okay. The system is in equilibrium under the action of a set of force is given a virtual displacement. The virtual work done by the forces will be zero. This is the principle of virtual work. But here you must see that we mention the equilibrium. So what is a virtual displacement? Virtual displacement is the imaginary infinitesimal variation of the coordinate, which is given instantaneously on that particular mass or the object. That is, during providing the virtual displacement, no time interval has been elapsed. This virtual displacement will be compatible with the system constraint. It will not violate the boundary condition of the system, how it is constrained with the ground. Forces acting on the system during virtual displacement will remain unchanged. Since there is no time is elapsed, there is no time to change the force, magnitude or direction during virtual displacement. The virtual work done is sum of the work done by the active forces under virtual displacement. Now, note that principle of virtual work is defined for the system under static equilibrium, but it is extended to the dynamic system by applying D'Alembert principle. How we will see that? Consider the same case of spring mass damper system. At any given instant of time, what are the different forces acting on it, active forces acting on it? Mg minus k delta plus x. Mg is the gravity force. K delta plus x in the opposite direction is the restoring force applied by the spring. By applying D'Alembert principle, we also mention this force minus mx double dot, which is the inertia force, not physically existing, but artificially brought into the picture. This inertia force is also acting. At that instant of time, x, we introduce a small virtual displacement delta x, that is small variation in the coordinate x in the object or the mass. Now this small variation will happen without any time spent, instantaneously. So what are the work done under this virtual displacement by different forces acting on it? Mg delta x minus k capital delta plus x into delta x minus mx double dot into delta x. And you see the delta x will be cancelled easily from each term. Total virtual work will be 0, delta x will be cancelled, and you will get back the same equation. So you will see this is obvious. This is why we need to readdress this situation again by virtual work. Now, I just readdress this situation that the virtual work principle will lead to the same equation. And this is shown for a very much simplified system. For a much complicated system, this pathway of deriving the equation of motion through virtual work principle will not be so much straightforward, but their philosophy is same. Particularly for multi-degree of freedom system, very difficult to analyze different component of actual physical coordinate which will contribute in different manner in a certain virtual displacement coordinate. You need certain geometric relationship. But here, for a single degree of freedom system, it is very much easy to show. Actually, from the virtual work principle, we derive Hamilton principle as well as Lagrange's principle, Lagrange's equation also. Now we will see the solution of the equation. Now we will see the solution of the equation. Is the undamped free vibration of a single degree of freedom system. You know this thing. I'm just recapitulating your knowledge. We have this equation of motion, mx double dot plus kx equal to 0. Now, if you divide the equation, both sides of the equation by m, you can write x double dot plus k by mx equal to 0. Now, this k by m is defined as the square of a quantity which is known as natural frequency. Why it is called natural frequency? Particularly why it is called frequency, we'll get that idea when you obtain the solution. Now, in this case, this omega n square, that is square of the natural frequency, it is a constant term. It is not varying with time. Also, it is not a function of any quantity x or x dot or x double dot. So that is why this equation can be considered as a linear, time invariant, ordinary, homogeneous differential equation. Linear, since the coefficient to different derivatives of the degree of freedom, coefficient to different derivatives of the degree of freedom is independent of the degree of freedom or its derivative themselves. Time invariant because those coefficients are independent of time. Ordinary differential equation because it is not a partial differential equation. It is differential equation with single independent variable time. Homogeneous differential equation because right hand side there is no forcing function. So this is the complete classification of this differential equation. Now we are entering in the domain of mathematics than in the domain of physics or mechanics. We'll deal with this mathematical equation. From the physical system, we converted a mathematical model. Now we'll deal with this mathematical model. Now, again, what is the order of this differential equation? The order is 2. So in order to completely solve this equation or in order to integrate it, we need at least 2 constants. That constant is called initial condition because here in the independent variable is time. Time t equal to 0, what is the condition of the system in terms of the coordinate and derivative of the coordinate? We need to define. Now, first we take the trial solution. You know how to take this. X as a function of time is x bar, which is independent of time, times e to the power lambda t. Lambda is a constant. X bar is also a constant. These 2 constants has to be determined. This is called separation of variable. We separate out the solution variable into 2 parts. One is independent of time, another is dependent of time. This is called amplitude. This is called time varying part. So x double dot is nothing but lambda square x bar e to the power lambda. Substituting this trial solution and this derivative, second derivative into the equation of motion, you will get an equation here. For non-trivial solution, lambda square plus omega n square will be 0. And solving for lambda, we'll get 2 roots of lambda, which is equal to plus minus j into omega n, where j is under root minus 1. So omega n is square root of k by m. So general solution of the vibration of this system governed by, defined by this governing differential equation is nothing but x as a function of time, which is a linear combination of 2 solutions, x1 bar e to the power lambda 1t, that is e to the power j omega t, x2 bar e to the power minus e to the power lambda 2t, that is e to the power minus j omega n t. Since this is a linear differential equation, this linear superposition of two solutions will give the general solution of the system. Now you can write e to the power j omega n t and e to the power minus j omega n t as into the sine and cosine component. That is, e to the power j omega n t will be cos omega n t plus j sine omega n t. E to the power minus j omega n t will be cos omega n t minus j sine omega n t. Now, making certain algebraic manipulation, we can express this solution as a sine omega n t plus b cos omega n t. A, B are two constant quantity that is independent of time, but they may be complex. Now, what is the actual form of A and B? That is defined by the two conditions which we have mentioned as initial condition. It is the state of the system at the beginning of the vibration. So we assume that at t equal to 0, the displacement x of the system is x0. We have displaced the system by an amount x0 at t equal to 0, then we have left it to vibrate. And at t equal to 0, velocity imparted on the system is x dot 0. So by the analysis, you apply this in this equation, you will find that A will be x dot 0 by omega n, B will be x0. So xt, total general solution of the free vibration of an undamped single degree of freedom system will be x dot 0 by omega n sine omega n t plus x0 cos omega n t. This is a purely oscillating motion. The amplitudes of oscillation you can find out by normalizing this. How you will normalize? You know how to convert a term which is a sum of a sinusoidal quantity and cosine quantity into a single function of either sine and cos. You just write down, just divide it by under root x dot 0 by omega n square plus x0 omega n square, and then you convert it into a sinusoidal term, single sinusoidal or cosine term. In that case, with omega nt, you will get a phase term. That phase difference will be expressed in terms of these two quantities. Yes, we'll just pause our discussion today here. Do you have any question? These are all recapitulation. I'm just revisiting what you have learned in your previous course. Any question?
Hello, sir. In the last expression, you told we can find the phase difference.
For a moment, I just have to put my cough down.
Okay.
Yes, okay. I have come back.
Yes, I didn't understand the last part about this last purely oscillatory motion equation. You said we can find the phase difference, but I didn't understand that part.
Okay. So can you do one exercise? If it is a cos theta plus b sine theta, or a sine theta plus b cos theta.
Yes.
Can you convert it into a single sine expression or single cosine expression?
Yes. Okay.
That I am mentioning.
Okay.
That is under root a square by b square. You divide the entire expression by that.
Okay, sir.
And then a by s under root a square by b square and b by under root a square by b. So you are assuming that this is a separate sine or cosine term, cos phi, and another is sine phi.
Okay, sir.
Then you
Thank
add them up
I got it.
according to the identity of trigonometry.
Mhm.
That I have understood. From that, you can understand that it is actually a single frequency expression. That frequency is omega n. That is why I am calling it is a
Okay,
purely oscillating.
Sir, I have another question about the Lagrangian equation.
Yes.
There, the first term is, I don't understand the physical significance of the first
Right.
term.
I only mention the physical significance because the Lagrange's expression is appreciated with much insight when we study multi-degree of freedom system. But in order to reach there, I have to go through the single degree of freedom system.
Yes.
So we do not keep our head heavy here. Now, the first expression, this expression del t del x dot within the bracket, you can take it as a generalized momentum of the particle. Generalized momentum. This is a very important term, generalized.
Okay.
Del t del x dot. Then ddt of del t del x dot is the rate of change of that generalized momentum.
Oh, okay. Okay. I get it. Thank you.
And q is the generalized force. When we'll discuss Lagrange's equation in details during the multi-degree of freedom system, we'll learn about this term in much details.
Okay.
We just mentioned the form. If you form a kinetic energy, potential energy from a system, then you apply directly in the Lagrange's equation in order to obtain the equation of motion. All right, so today we'll conclude here. We just take the attendance today. Yes, I shall share the PDF. I just finish this part. After that, I shall share the PDF. So it will take, yes. I will share the recording. I will directly share the recording. For initial few days, you just go through the recording. After I finish this part, it's a single degree of freedom free vibration. I will share automatically these notes. Okay. Roll 51. Moinak Tudu. Roll 60. Khizir Alam. Roll 117. Pradeep Kumar Bera. 118. Utpal Singh.
Yes, sir.
119. Monish Das. Okay. 121.
Present, sir.
Okay. 22.
Present, sir.
Okay.
Hello,
23.
sir. One,
Pradeep Kumar Bera.
yes, sir. 117.
Yes, okay. It is given.
Yes, sir.
123. Saurabh Mondal. 123. Okay. 126.
Yes, sir.